Here's our first problem. We have two masses. Mass number 2 is hanging over a pulley, and it falls and pulls along with it mass number 1. Mass number 1 is 15 kilograms. Mass number 2 is 5 kilograms. And they're asking us to find the net force on the system, the acceleration of the system, and the tension in the string. So let's begin by making a force diagram of the entire system. What does that mean? That means I'm treating blocks 1 and 2 as a single object. There are two blocks connected with a string, and that is one object. So the pulley, remember, all the pulley does is change the direction of the force. So this force of block number 2, as gravity pulls down on it, the tension in the string is transferred to a horizontal force by the pulley. So that allows me to say the string is my x-axis. And so you can see here are the forces acting on block number 1. Gravity is pulling down on it, and the table is supporting it with the normal force. But both of those forces are in the y direction. And the tension in the string is pulling block number 1 to the right, and that comes from the weight of block number 2. So my only force in the x direction then is the weight of block number 2 pulling down on the right, but that transfers to a horizontal force over here. So when I look at some of the forces in the y, using Newton's second law, that's here. There is no acceleration in that direction off or into the table. So that's acceleration of 0. So the normal force points upward. The weight of number 1 points downward. So I get Fn1 minus m1g is my sum of the forces in the y direction, and that equals 0. And from that, I can see that the normal force is equal to the weight of block number 1, and that turns out to be 147 newtons. In the x direction, you see here, I'm letting the string be my x-axis, so that's why it is curved like this. And the positive direction is the direction of motion. That's the direction I've chosen to be positive. And that is the only force in the x direction. Tension in the string is an internal force, because remember, I'm looking at this, both blocks in the string, as one object. So for the entire system, tension is inside the system, so that's an internal force, and it doesn't count for my sum of the forces in the x direction. So the weight of block 2 is the only force along this x-axis. And so that is my only force, m2g. And now that is accelerating the system. How much mass is in the system? m1 plus m2. I'm going to plug in the numbers that I know. There we go. And A, the acceleration of the system, is the only thing I don't know, so I can solve for that variable. And you can follow the math. You see that that comes out to be 2.45 meters per second squared. So that is my acceleration of the system. And along the way, we found out that the net force, right, the net force, that is the net force that is accelerating the system. You can see here, these forces cancel each other out in the y direction. Their sum is 0. So all that's left over is the net force, which is in the x direction, in the direction of motion, and that is the weight of number 2. So my net force is 49 newtons, the weight of block number 2. Next, they're asking us to find the tension in the string. So now I need to treat the blocks separately, because when I do that, now the tension in the string is an external force to each block. So here I've shown the forces acting on mass number 1, just as before, the normal force of the table and the weight of gravity caused by gravity. But now the tension is an external force, so I include it in my force diagram. And over here, the tension in the string pulls up on mass number 2, and gravity pulls down. So I can look at either block. On block number 1, there is only one force in the x direction, and that is the tension. And so that force is equal to mass times acceleration, but now I'm only considering block number 1. So it is no longer the mass of the whole system, but only the mass of block number 1. There we go, 15 kilograms. I found the acceleration up here in the first part, 2.45. So there is my tension in the string, 15 times 2.45, or 36.75 newtons. That is probably the simplest way to find the tension, but you can find it using block number 2. Block number 2, the sum of the forces acting on it is equal to its mass times acceleration. But now on block number 2, there are two forces in the direction, or along the direction of motion. M2G is in the positive direction, according to my plus-minus system up here. And the tension is in the negative direction, so M2G minus Ft is my sum of the forces. And those are the forces acting on mass number 2. So I use M2 for the mass in my equation. And now I can plug in all the numbers that I know and solve for Ft, which, of course, I still get the same answer, 36.75 newtons, that I did using block number 1. In problem number 2, we're pushing 2 blocks with a force of 45 newtons. The force is applied to block number 1, which then pushes into block number 2. So you can see here block number 1 is 6 kilograms, block number 2 is 9 kilograms. So this internal force, when I push on block number 1 pushes on block number 2. So that'll be called F6 on 9, because the 6 kilogram block is pushing on the 9 kilogram block. So if we say M1 pushes on M2 action, then the reaction is M2 pushes back on M1, and that'll be F9 on 6. And that is an action-reaction pair. So I know from the beginning that F6 on 9 and F9 on 6 are going to be the same value. Let's take a look at the solution here. I start off by drawing a force diagram, and my force diagram I'm going to start off by doing it on the entire system. That means I'm going to treat M1 and M2 as a single thing, as a single mass. So you see here I've drawn a dot to represent both blocks as a single object, and that object's mass is M1 plus M2, both of them, or 15 kilograms. And the force that is accelerating that 15 kilograms is 45 newtons. So using Newton's second law, the sum of the forces is mass times acceleration. There is my force, 45 newtons, mass 6 plus 9, or 15 kilograms. So when I do that math, I see the acceleration of those 2 blocks is going to be 3 meters per second squared. Now to find the internal forces, what is the force in between the blocks? Now I want to treat them individually or separately. So I'm showing you here, block number 1 has the 45 newtons pushing from the left, and then block 2 pushing back on block 1 is my force on the right side of block 1, and I call it F21 for the force of 2 on 1, which is the same as 9 on 6. Okay, so the sum of the forces then, assuming to the right is the positive direction, F1 will be positive and F2 on 1 will be negative. So here you see my sum of forces, and remember, these are the forces acting on only block 1. So I only use the mass of block number 1 here, which is 6 kilograms. I know F1 is 45. I know the acceleration from the very first part of the problem that I found was 3 meters per second squared. So I can solve for the force of 2 on 1, and that comes out to be 27 newtons, which is also on the sheet referred to as F9 on 6. That's 27 newtons. Now, if I had used block number 2, now block number 2, the internal force between the 2 blocks, which I call the force of 1 on 2, that is the only force accelerating block number 2. So when I say my sum of the forces, now F1 on 2 is the only force in the x direction, and those are the forces acting on just mass 2. So that's the mass I used, the mass of block number 2, 9, and the acceleration was 3, of course. So I still get 27 newtons for 1 on 2, or F6 on 9. And like I said at the beginning, we expect those to be the same, and they are 27 newtons. Now, what is the net force on the 6 kilogram block? That is block number 1. So I'm going to look at block number 1, or the 6 kilogram block, and I know that its mass is 6 kilograms, and I know it's accelerating at 3 meters per second squared, so that tells me the net force acting on the block must be F equals ma, 6 times 3, or 18 newtons. I could have done it another way. I could have looked at the forces acting on the block number 1. I found that up here, F21 was 27 newtons to the left, and F1 was 45 newtons to the right. So there's the force diagram of those forces acting on block number 1. And if I sum the forces, 45 plus negative 27, I still get 18 newtons. So there were 2 ways I could have found the net force on block number 1, or block 6 kilograms. 18 newtons. Our third problem, we have 2 blocks connected by a string, and we're pulling them both along with another string from the far right. And this is the net force accelerating the system. We're asked to find that, and we're also asked to find the tension in the string when block number 1 has a mass of 7 kilograms, block 2 has a mass of 5 kilograms, and they are being caused to accelerate at 6 meters per second squared. Okay, so like before, I'm going to treat both blocks tied together with a string as one object. So my entire system then has a mass of m1 plus m2, and it's being accelerated by this net force over here on the right. So that allows me to quickly solve for the net force, because I know the mass of both blocks, and I know the acceleration of the system, 6 meters per second squared. So the total mass, 12, times the acceleration, 6, tells me the net force must be 72 newtons. What is the tension in the string? Well, that is a force that acts on each block separately. So here's block 1. The tension in that middle string is the only force pulling on block 1. But on block 2, the net force pulls to the right on block 2, and the tension in the string pulls to the left on block 2. So I can use either one of these to find the tension in the string. You're going to see that using block number 1 is the simpler of the 2 ways, because there's only one force, and so there's only one unknown in my equation here, and it's a simple F equals ma, where Ft is the force, m1 is the mass, and both blocks are accelerating at 6 meters per second squared. So mass 7, acceleration 6, the tension in the string is 42 newtons. If I had chosen block number 2, however, now I've got the net force in the positive direction, the tension in the string is in the negative direction, so there's my sum of forces, and now those are the forces that act together to accelerate mass number 2, which is 5 kilograms. So the net force was 72 that I found in the very beginning, and the mass of number 2 is 5, the acceleration is 6, so I can solve that equation for the tension in the string, and I get the same answer that I got over here, 42 newtons. Okay, number 4 is very similar to number 3, but now I have 3 blocks tied together with 2 different strings, but same kind of situation. I'm pulling all 3 blocks with the net force over here on the far right, and then this tension in this string will accelerate blocks 1 and 2 only, and the tension in this string will accelerate block 1 only. And of course, the net force over here is accelerating all 3 blocks. The masses of the blocks are given, and they tell me what the net force is. Find the acceleration and the tension here between 1 and 2, and the tension here between 2 and 3. Okay, so here's my force diagram up at the top. This force diagram is when I treat each block independently, but when I solve for the entire system, remember that's treating it as if 1, 2, and 3 are a single object. So the total mass of that is the sum of all their masses, and the net force over here on the right that's pulling all 3 of those masses is 90 newtons. So I can use my Newton's second law equation to find the acceleration, and that is 4.5 meters per second squared. Now to find the tensions in the strings, I need to treat the blocks separately. So here's the first block. It is only being pulled by tension in string number 1. Mass number 2 has a string on either side of it, so tension number 1 pulls to the left on it, and tension number 2 pulls to the right on it. And then mass number 3, the net force is pulling to the right, and the tension number 2 in the string is pulling to the left. So if I start with this one, because there's only one force acting on it, that's going to make it a little easier. So the tension is the only force pulling on that mass number 1. So mass number 1 is 5 kilograms. I already found the acceleration was 4.5 meters per second squared. So I can solve for the force of tension in string number 1, 22.5 newtons. Now that I know that, I can use that here because these two are an action-reaction pair in the string between M1 and M2. So I know what T1 is. My sum of the forces on M2 is T2 to the right, positive, and T1 to the left, negative. So there's the sum of the forces, and I've already found T1. So I can plug that number in. I know the mass of block number 2 is 11 kilograms. I found the acceleration of the system, 4.5. I can solve that for T2. There's the math, and I get 72 newtons. If I had chosen mass number 3, I could have found T2 that way as well. Now the sum of the forces is F net to the right in the positive direction and T2 to the left in the negative direction. So there's the sum of forces on mass number 3. So of course I use the mass of number 3 in the equation, and all the blocks are accelerating at 4.5 meters per second squared. So I plug that in for A. I can solve for T2 now, and I get the same answer that I got using block 2. So you can use either one. In number 5, it's a 3-mass system. M3 is the one hanging over the pulley. So recalling from number 1, the weight of M3 is going to be the net force that accelerates the system. The weights of M1 and M2 are perpendicular to the direction of travel, so their weights will not contribute to the motion of the system, only the weight of number 3. The masses of the blocks are given, and we're asked to find the acceleration. And once again, the tension here, Ft1, and the tension over here, Ft2. Note that, remember, the pulley only changes the direction of the tension force. So the tension right here is going to be the same as the tension here. All along this piece of string, the tension will be Ft2, the same value. So let's look at the solution. Here we go. My force diagram for each individual block shows the forces, both in the X and the Y direction. We'll come back to that because first we're going to treat this as a single system, where M1, M2, and M3 is the mass of the system, and the net force accelerating that system is only the weight of number 3. These tension forces T1 and T2 are internal when I treat it as an entire system, so the only force in the direction or along the x-axis, which curves around the pulley, is the weight of block number 3. So that's what you see down here. M3 times G is the weight of block 3. That is the force, the sum of the forces in the x direction. It's the only force in the x direction. And that is accelerating this much mass, which is the whole system. M1 plus M2 plus M3. And the acceleration is what I'm solving for. So you can see there, when I do the algebra, I get 1.96 meters per second squared for the acceleration of that entire system. Now to find the tensions in the strings, I have to treat each block separately. So number 1, I showed the Y direction. I don't really need to know that information. But if this was a friction problem, then I would need to know the normal force, and that is how I find it right there. On a horizontal surface with no other forces in the Y direction besides the normal force and the weight, the normal force is always equal to the weight. Okay, but in the X direction, tension in string number 1, if we look back at our force diagram, right here, tension in string number 1 is the only force that's accelerating block number 1. So my sum of the forces then on number 1 is T1, and the mass of that is mass 1, and I found the acceleration 1.96, so I can solve for the tension in that string between M1 and M2. It is 9.8 newtons. And just like in problem number 3, I can either look at block number 2 or block number 3 to find the tension in the string T2 because they are forces acting on either of those blocks. On block number 2, T2x to the right, so it's positive, and on block number 3, T2x to the left, so it's negative. And of course, F net is to the right and positive on block 3, where T1 is to the left, so it's negative on block 2. So you can see that's what my signs are, positive T2 and negative T1 for block number 2, and the weight of block number 3 is in the positive direction on block 3, and T2 is in the negative direction on block 3. So those are the sum of the forces, and on block 2, those sum of forces are accelerating mass number 2, and in number 3, those sum of the forces are accelerating mass number 3. So I use those values for mass in that equation, and you can follow the math along here, and I get the same answer regardless of which block I use for the tension in string number 2, 39.2 newtons. Number 6, this setup is called an Atwood's machine, and we have 2 blocks hanging over a pulley. So the tension in the string is the same on both sides because the pulley is just changing the direction of that tension. And the net force will be the difference of the 2 weights because they pull in opposite directions. So they are fighting against one another. So the difference of those 2 weights will be our net force. Here's the information that's given. We're asked to find the acceleration and the tension in the string. So let's take a look at the solution. Okay, so here's the force diagram. The weight of mass number 2 on the right is pulling down, and the weight of mass number 1 on the left is pulling down. Since the mass of number 2 is greater than the mass of number 1, we know that it will rotate clockwise. M2 will fall and M1 will rise. So I've chosen the positive direction to be the direction of motion. So that means my weight of block 2 is in the positive direction and my weight of block 1 is in the negative direction. So when I look at the entire system, my sum of the forces is the weight of number 2 in the positive direction, the weight of number 1 in the negative direction, and that sum of forces right there accelerates the total mass of the system, 8 plus 6. And so I plug in all the numbers and solve the equation for acceleration, and I see I get an acceleration of 1.4 meters per second squared. What is the tension in the string? Now I can look at either block separately. So when I do that, here's my force diagram for block number 1. Here's my force diagram for block number 2. So for block number 1, tension is in the positive direction, the weight is in the negative direction, and that sum of forces on block number 1 accelerates number 1. And I have solved this equation for tension, and I'll tell you why here. Number 2, I'm going to do the same thing. The weight of number 2 is in the positive direction, and the tension is in the negative direction. So there's the sum of forces that's accelerating mass number 2. And I've solved that equation as well for tension. What am I showing you here? Well, mass number 1 is accelerating upward. So to accelerate upward, I know the tension has to be larger than the weight. And that's what this equation is showing us here. The tension is the weight plus M1A. So the tension is more than the weight by this amount. And block number 2 is accelerating downward. So I know the downward force has to be larger than the upward force in order for it to accelerate downward. And that's what we see here. The tension, which is the upward force, is less than the downward force, the weight, by this much. So the tension is less than the weight of number 2, and it is more than the weight of number 1, which makes sense because number 1 is accelerating upwards and number 2 is accelerating downwards. And when I solve those equations for the tension, of course I get the same value for tension no matter which block I use. The tension in the string is 67.2 newtons.